Welcome to this presentation on monolithic architecture, part of our detailed exploration of architectural patterns. In this session, we will dive deep into what monolithic architecture is, its benefits, drawbacks, use cases, and how it compares to other architectural patterns. Monolithic architecture refers to a unified software design where all components are tightly integrated and deployed as a single unit. This approach has three key characteristics: a single code base, a single deployment unit, and tightly coupled components, making it simple to develop and manage early on. However, as the system grows, these same characteristics may become limiting factors. Let's look at the benefits. One of the main advantages of monolithic architecture is simplicity. It's easy to develop and deploy, particularly in small projects. It also provides performance efficiency due to its reduced latency from fewer network calls between components. Debugging and testing are simpler because the entire application resides within a single unit. Additionally, monolithic applications tend to have lower initial development costs, making it ideal for startups and or small applications. Despite these benefits, monolithic architecture also comes with several drawbacks. Scalability becomes challenging as the application grows. Updating or deploying a new feature can be slower because everything is part of a one single large unit. It also offers limited flexibility when trying to adopt new technologies. Moreover, a bug in any part of the system can affect the entire application, creating a single point of failure. This makes continuous deployment and testing difficult in large-scale environments. Monolithic architecture works well for small to medium-sized applications with stable requirements. Examples include simple websites, blogging platforms, and small e-commerce systems. It's also suitable for early stages of product development where the focus is on rapidly prototyping ideas. Lastly, legacy enterprise applications that have a well-established architecture often retain monolithic designs due to scalability and consistency. Some classic examples of monolithic applications include early versions of WordPress and Magneto, where which were developed as single unified systems. Small-scale e-commerce platforms where components like the product catalog, payment systems, and user authentications are all bundled together also fits this model. Lastly, traditional ERP systems are a great example where all business operations are centralized into a single monolithic application. Let's take a closer look at a case study of a monolithic e-commerce platform. Imagine an application with product catalogs, shopping carts, order processing, and user authentication all tied together in a single package. The key benefit of such system is its simple implementation and the ease of debugging. However, as traffic increases, scaling the system to handle peak times can become difficult. Also, bugs in one module can disrupt the entire platform, leading to significant downtime. Now let's compare monolithic architecture with other patterns like microservices and event-driven architectures. While monolithic systems are simpler to develop, they face scalability challenges as the system grows. Microservices, on the other hand, break down the application into smaller independent units, allowing better scalability. Event-driven architectures enable asynchronous communication, making them more flexible and responsive compared to the synchronous nature of monolithic systems. In conclusion, monolithic architecture is an ideal choice for small-scale applications or those with stable, unchanging requirements. It provides simplicity and cost effectiveness in the early stages of development. However, as the application grows and becomes more complex, transitioning to more modern architectures like microservices or cloud native designs might become necessary to ensure scalability and flexibility. That concludes our overview of monolithic architecture. I hope this gives you a solid understanding of these features, benefits, and limitations. If you have any questions or would like to discuss specific use cases or comparisons, feel free to ask. Welcome to the presentation on microservices architecture. This is our day 9 in our detailed exploration of architectural patterns. Let's dive into understanding how microservices can transform application development. Microservices architecture is a design style where an application is broken down into smaller, independent services. Each of these services is focused on a specific business function and they communicate via lightweight protocols like REST or gRPC. This centralized approach, this decentralized approach offers flexibility and scalability for modern applications. When comparing microservices to monolithic architecture, the differences are clear. In monolithic design, the application is a single, tightly coupled code base, which can make scaling and maintaining it difficult. Microservices, on the other hand, offer independent services with decentralized databases, which allow for easier scaling and maintenance. The flexibility to choose different technologies for each service is a huge advantage. Microservices come with several benefits. They allow independent development and deployment, making it easier to manage services in isolation. They are scalable, meaning you can increase resources for only the high demand services. With technology diversity, teams can use different technologies for each service. Additionally, microservices provide fault isolation, ensuring that one service failure does not affect others. Overall, they promote agility and flexibility in development. However, there are challenges with adopting microservices. For instance, the system complexity increases due to the need to manage multiple services, each running independently. Distributed system issues such as latency and ensuring consistency can also arise. Handling data management becomes more complex, and the overhead of inter-service communication can introduce delays. To, to address this, robust CI/CD pipelines and monitoring tools are essential. One of the main strengths of microservices is their scalability. Services can be scaled horizontally, meaning individual services can be expanded based on their specific load, ensuring efficient resource usage. Tools like Kubernetes and AWS Lambda support auto scaling, allowing services to scale up or down in response to demand. For example, a payment service may need to scale during high traffic periods, while a recommendation engine scales during user activity peaks. Several tools and technologies support the microservices architecture. API gateways like Nix and AWS API gateways handle routing and security. Communication between services often uses protocols like REST or gRPC. Service discovery tools such as Eureka and Consul help services find each other in dynamic environments. Containerization platforms like Docker and Kubernetes provide the foundation for managing microservices. Monitoring and logging tools, including Prometheus and the ELK stack, help maintain observability in distributed systems. Many companies have successfully adopted microservices. For example, Netflix utilizes microservices to manage different aspects of streaming, recommendation, accounts, and billing. Amazon breaks down its application into microservices for product search, recommendations, and order management. Uber uses microservices for managing ride requests, pricing, notification, and payments. These companies benefit from the scalability, resilience, and agility provided by microservices. To make the most of microservices, it's important to follow best practices. Define clear service boundaries using domain driven design to ensure services are focused and cohesive. Implement DevOps practices with CI/CD pipelines for seamless updates. Focus on resilience by using retries, circuit breakers, and fallback mechanism to ensure the system remains robust. Additionally, use centralized logging and monitoring tools to maintain visibility into the system's performance. Lastly, microservices often rely on eventual consistency models instead of strict consistency. To conclude, microservices offer great flexibility, scalability, and fault isolation, making them a powerful tool for building large scale distributed systems. While the architecture introduces complexity, the benefits far outweigh the challenges when implemented correctly. Companies like Netflix, Amazon, and Uber have demonstrated the power of microservices in real world applications. By following best practices, microservices can be a game changer for modern software development. Welcome to today's presentation on client server architecture, an in-depth exploration of this foundational software design pattern. Let's dive into its structure, components, benefits, and challenges. Server architecture is a software design model where clients make requests for services or resources, and servers provide those services in response. The core idea here is that the client initiates the request and the server responds with the necessary data or action. Key features of this model include decoupling responsibilities, scalability, resource sharing, and interoperability across platforms. The architecture is composed of three primary components: the client, the server, and the communication mechanism. The client is responsible for requesting services such as web browsers or mobile apps. The server is the provider of those services like web servers or database servers. The communication between them happens through protocols such as HTTP or TCP/IP, with data exchanged in the format like JSON or XML. In server architecture, the communication typically follows a request response cycle. The client sends a request and the sender responds and the server responds. Communication can be either synchronous or is asynchronous. In synchronous communication, the client awaits for the server's response, while in asynchronous communication, the client can continue processing while waiting. One key aspect of this architecture is statelessness, meaning each request is independent, such as how HTTP works. Client server architecture offers several advantages. First, it allows for centralized control, making resource management easier. Maintenance is simplified because updates are typically performed on the server side. Clients can share resources efficiently, and the architecture is scalable, meaning servers can be upgraded to accommodate more clients as needed. However, there are some drawbacks. One major issue is the single point of failure. If the server goes down, all clients are impacted. Performance bottlenecks can occur if too many clients overwhelm the server. Additionally, there is a dependency between clients and the server. If the server becomes unavailable, clients cannot access services. Client-server architecture is widely used in various domains. For example, in web applications, clients like browsers fetch data from web servers. In email services, clients like Outlook interact with SMTP, IMAP servers. It's also common in database access where applications query database servers. Multiplayer games also rely on client-server models for real-time interactions. Looking ahead, client-server architecture is evolving. Many systems are moving to the cloud for better scalability and resource management. Additionally, hybrid models combining client-server with microservices are becoming more popular. As security concerns grow, enhanced security features like end-to-end encryption and multi-factor authentication are being implemented. To conclude, client-server architecture continues to be the backbone of many modern systems, balancing the benefits of scalability, resource sharing, and centralized management. As technology evolves, this architecture adapts with advancements like cloud computing and hybrid models. Thank you for your attention. Welcome to this presentation on layered entire architecture. Today we will explore the components and interactions that make up this widely used software architectural pattern. Let's dive in. So what is layered architecture? It is a design pattern where the application is divided into separate layers, each with its own specific role and responsibility. This separation of concerns allows for better scalability, maintainability, and flexibility, making it easier to manage complex systems. In a typical entire architecture, there are four key layers: the presentation layer, which manages user interfaces; the business logic layer, responsible for core application logic; the data access layer, which handles communication with the database; finally, the database layer, where data is stored and retrieved. Let's start with the presentation layer. This layer is responsible for the user interface and user interaction. It handles tasks like displaying data and collecting user input. Technologies such as HTML, CSS, JavaScript, and frameworks like React or Angular are commonly used here. A great example would be the web or mobile interfaces of an online store. Next, we have the business logic layer, which sits at the heart of the application. This layer processes the core application rules such as data validation, business rule enforcement, and processing user requests. Technologies like Java, Python, Node.js, or C++ are typically used in this layer. A real-life example would be an order validation system in an e-commerce application. The data access layer is responsible for handling all interactions with the database. It executes queries, manages transactions, and ensures data retrieval and updates. Technologies like object relational mapping (ORM) frameworks such as Hibernate or Entity Framework are often used. A good example would be fetching customer details or product information from the database. The database layer is where data is stored. This layer ensures data persistence and is where operations like indexing and backups occur. It can involve both relational databases like MySQL or PostgreSQL or NoSQL databases like MongoDB. Think of it as the underlying data storage for applications such as customer data in an e-commerce system. Now let's Now how does layered architecture fit into high-level design? Here's a simple breakdown. Define the different layers: presentation, business, data access, and database. Specify the responsibilities for each layer. Indicate how data and control flow between the layers. Ensure scalability and flexibility in the design to handle future changes. Here's an example of how this might work in a real-world e-commerce system. The presentation layer would include the user-facing elements like the website or mobile app. The business logic layer would handle things like order processing and payment calculations. The data access layer would provide APIs to fetch product details, while the database layer stores customer orders and product catalogs. So why should we use layered architecture? Here are some of its benefits. Separation of concern. Each layer is focused on a specific aspect, making development and debugging simpler. Reusability. Layers can be reused across projects, saving development time. Scalability. Each layer can be scaled independently depending on the needs of the application. Flexibility. You can use, update, or replace layers without disrupting the entire system. Testability. With clearly defined layers, it's easier to test each component in isolation. While there are many benefits, layer architecture also comes with challenges. Performance overhead. The use of multiple layers can introduce some latency due to data passing through each layer. Complexity. Managing dependencies between layers can become complex in large systems. Rigidity. The structure can make it difficult to rapidly prototype or adapt to quick changes. Over-engineering. For smaller projects, this architecture might be more complex than necessary. Let's look at a couple of real-world examples where layered architecture is used. In a banking system, the presentation layer could be a mobile or web application. The business logic layer would process transactions, while the data access layer would handle APIs and the database layer would manage core banking data. For an e-commerce application, the presentation layer would be the online store interface. The business logic layer handles order processing. The data access layer interacts with product data, and the database layer stores customer orders. To conclude, layered architecture is a powerful design pattern that helps build scalable, maintainable, and testable applications. By separating concerns into distinct layers, it provides a clean structure for both development and maintenance. Understanding how each layer interacts will help us implement this architecture effectively in our own projects. Now I would like to open the floor for any questions. Feel free to ask about anything related to layered architecture, its components, or its implementation. I am happy to clarify any doubts. Welcome to this presentation on Event Driven Architecture, or EDA. Today we will explore the key concepts, components, and benefits of this powerful architectural pattern and understand how it supports scalable, flexible, and real-time systems. Event-driven architecture is a system design approach where components communicate by producing and consuming events. These events represent state changes, user actions, or external triggers, enabling the system to react in real time. The main strength of EDA is its asynchronous nature, ensuring that components remain loosely coupled and independent. EDA has several key characteristics. Asynchronous communication. It allows components to function independently without blocking the flow of other tasks. Loose coupling. This reduces the dependencies between components, making it easier to scale and modify individual parts of the system. Real-time processing. EDA systems react to events as soon as they occur, making them ideal for applications requiring quick responses. Scalability and flexibility. As each component operates independently, it's easy to scale them as demand grows. EDA is widely used in various industries. For example, in e-commerce, events like order placements or payment completions trigger actions like inventory updates and shipping notifications. In financial services, real-time event processing enables fraud detection and transaction monitoring. IoT applications use EDA to handle data from sensors and devices, while social media platforms react to user activities like posting or event or commenting through notifications. Event-driven systems are built with three essential components. Event producers. These components generate or detect events like a user placing an order or a system encountering an error. Event consumer. These components listen for and process events. For instance, a payment service may process a payment once an order is detected. Event brokers. Brokers like Kafka or RabbitMQ distribute events from producers to consumers, enabling seamless communication between different components. Event producers are responsible for detecting or creating events. They could be triggered by system actions, user input, or external systems. For instance, in an e-commerce platform, the producer would generate an event when a customer places an order. This event then travels through the system for further processing. Event consumers are components that listen for and react to events. When an event occurs, such as an order being placed, the consumer processes the event by executing business logic. In our e-commerce example, the shipping service could consume the order placed event to initiate the shipping process for the customer's order. Event brokers are the middleman that manages the flow of events between producers and consumers. They ensure that events are delivered to the appropriate consumers and handle message persistence in case of failure. Popular event brokers include Kafka, RabbitMQ, and Amazon SQS, each offering different features for event routing and management. Event-driven architecture offers numerous benefits. Scalability. Each component can be scaled independently based on load. Decoupling. Components are less dependent on each other, making the system more flexible and maintainable. Real-time responsiveness. The system reacts to events as they happen, ideal for real-time applications. Resilience. Fault tolerance is enhanced since events can be stored and reprocessed if needed. Flexibility. The architecture allows the easy addition or removal of components without disrupting the system. However, EDA goals does come with its challenges. The challenges include complexity. Designing and managing asynchronous communication can add complexity to the system. It also have challenges in debugging and monitoring. Identifying and troubleshooting issues can be difficult without proper tools. Latency is one of its challenges as delays in event processing might impact time sensitive applications. Duplication, ensuring that events are processed exactly once and handling potential duplication adds complexity. Various tools and technologies supports EDA. Event brokers like Kafka, RabbitMQ, and Amazon SQS are essential for managing event flows. For frameworks, we have Spring Cloud Stream for Java-based systems and AWS Lambda for serverless event-driven applications. Additionally, Avro and protocol buffers are commonly used for defining event schemas, ensuring consistency across the system. Let's take a look at a real-life example, a food delivery application. The system consists of event producers such as the customer placing an order, events broker like Kafka, which routes the order event consumers such as the payment service processing payments, the restaurant service notifying the restaurant, and the delivery service assigning a delivery driver. These components work in sync, processing the event in real time to fulfill the customer's order. When implementing EDA, here are some best practices. Design for idempotency. Ensure events can be processed multiple times without unintended consequences. Use standard event structures. Use tools like Avro or protocol buffers to ensure uniformity in event format. Monitor and log events. Effective monitoring ensures smooth operation and helps troubleshoot issues when they arise. Handle failure gracefully. Use retries, dead letter queues, and other strategies to manage failed events without causing system breakdowns. In summary, event-driven architecture is a powerful approach that enhances scalability, flexibility, and responsiveness. By decoupling components, EDA allows for real-time processing, enabling applications to react immediately to state changes. While there are challenges, especially around complexity and event management, the following best practices can help build robust, maintainable, and scalable systems. Thank you for your attention. I would now like to open the floor for any questions or further discussion on event-driven architecture. Welcome to the presentation on cloud native design. In today's session, we will be diving deep into cloud in architecture principles, serverless and containerized environments, and how they contribute to building scalable, efficient, and resilient applications. Here's what we will cover in today's presentation. We will start with an introduction to cloud native design, followed by the core principles of cloud architecture. Then we will look into serverless architecture and containerized environments. Finally, we will compare the two models and finish with a practical example of a cloud native application. Cloud native design is all about building applications that are designed for the cloud. This approach focuses on scalability, resilience, automation, and leveraging microservices and DevOps practices. A key benefit is the pay as you go model, which helps to optimize cost efficiency. Cloud architecture operates on a few key principles. Scalability ensures applications can grow with demand. Resilience is achieved through distributed systems that recover from failures. Automation enabled by infrastructure as code and CI/CD pipelines helps reduce manual tasks. Microservices allow flexibility and DevOps practices speed up development and deployment. The pay as you go model enables cost optimization. Serverless architecture is a cloud computing model where developers don't manage infrastructure. Cloud providers handle the servers. Key features of serverless computing include no server management, event driven design, auto scaling, and a pay per use pricing model, making it ideal for dynamic workloads. The benefits of serverless architecture include reduced operational complexity, faster time to the market, and cost efficiency, especially for applications with unpredictable or spiky traffic. By eliminating infrastructure management, developers can focus on writing code rather than worrying about the servers. However, serverless architectures do come with their own challenges. These include limited execution times for functions, cold start latency, and difficulty with debugging and monitoring distributed systems. These complexities need to be addressed when considering serverless for your application. Serverless architecture is ideal for use cases such as APIs and webhooks, background tasks like image processing, and real-time data stream analytics. It provides an efficient way to handle tasks that don't require constant server uptime. Containerized environments use containers to package applications and their dependencies. Containers ensure that applications run consistently across different platforms. They are lightweight, portable, and isolated from the host environment, providing a solution for scalable and efficient application deployment. The key benefits of containerized environments include consistency across different environments, facilitating microservices based architectures, and simplifying scaling through orchestration tools like Kubernetes. Containers help isolate applications, ensuring that they run the same way regardless of where they are deployed. However, there are challenges with containerized environments as well. These include the complexity of orchestration, especially when using tools like Kubernetes, container sprawl, and the need for expertise to deploy and manage containers effectively. These challenges should be considered when choosing containers for your applications. Containerized environments are well suited for migrating legacy applications to the cloud, implementing microservices based architectures, and setting up continuous integration and continuous deployment pipelines. They provide flexibility and scalability for modern application development. Now let's compare serverless and containers. In terms of infrastructure management, serverless is fully managed by cloud providers, while containers are managed by development teams. Serverless is auto scaling, while containers require orchestration tools like Kubernetes for scaling. From a cost perspective, serverless follows a pay per execution model, while containers charge based on running instances. Customization is limited in serverless but highly customizable in containers. Let's take an example of a cloud native application, an e-commerce platform. The front end could be deployed using serverless technologies like AWS Amplify, while the backend runs in containers with Docker and Kubernetes. Payment processing can be handled by serverless functions triggered by API calls, and scaling can happen dynamically during peak traffic, like during sales event. To conclude, cloud native design offers a powerful way to build scalable, flexible, and resilient applications. Whether you choose serverless or containers depends on your application's specific needs. Both approaches allow for faster deployment and development, easier scaling, and better resource utilization. Thank you for your attention. If you have any questions or would like to discuss the topic further, please feel free to ask. Welcome to today's presentation on comparison of architectural patterns. In this presentation, we will explore various architectural patterns, comparing their strengths, weaknesses, and ideal use cases. Before diving into the comparison, let's quickly recap the architectural patterns we have covered in previous days. Monolithic, microservices, client server, layered, event driven, and cloud native designs. Each of these patterns has unique characteristics that make them suitable for different scenarios. Here's a comparison matrix where we will look at various factors like scalability, de- deployment flexibility, fault tolerance, and the best scenarios for applying each pattern. This will give us a visual overview of how these architectures stack up against each other. Monolithic architecture is a traditional model where the entire application is developed and deployed as a single unit. While it's simple to develop and deploy, it lacks scalability, and as the app grows, it becomes harder to maintain. Monolithic systems are great for small to medium sized applications but can face challenges in handling large scale projects. Microservices architecture is a modern approach where the system is broken into smaller, independent services. Each service is focused on a specific functionality, making the system more scalable and fault tolerant. However, managing microservices can be complex, requiring advanced orchestration tools. This pattern is ideal for large, dynamic systems with frequent updates like e-commerce platforms. In client-server architecture, the client requests services from a centralized server. This separation of concerns allows for flexibility as multiple clients can interact with the server. However, the system can be affected by latency and network issues, especially in high traffic environments. It's widely used in web applications and file sharing systems. Layered or entire architecture divides the system into distinct layers such as presentation, business logic, and data access. This modularity makes the system easy to maintain and extend. However, it introduces performance overhead and can increase complexity as more layers are added. This approach is commonly used in enterprise level applications. Event driven architecture is based on the idea of producing and consuming events. Systems react to changes in real time, making this pattern highly responsive. While it offers great scalability and decoupling, debugging and testing can be challenging. It's suitable for real-time applications like stock trading platforms or IoT systems. Cloud native design focuses on building applications that fully leverage cloud environments. This includes serverless architectures, which minimize infrastructure management, and containerized environments that ensure portability. Both offer scalability, but the choice depends on the specific needs of our application. Cloud native is a great option for scalable cloud hosted solutions like media streaming. Choosing the right architecture requires considering factors like the size and complexity of the application, the expertise of your team, scalability requirements, and budget. For instance, if we are working on a small project with a limited budget, a monolithic approach might be best. But for a large scale dynamic system, microservices could be more effective. Let's look at some real world scenarios. Monolithic architecture works well for small e commerce websites. Microservices for large platforms like Netflix, client server for web services, event driven for stock trading, and cloud native for cloud hosted platforms like Spotify. Understanding these use cases helps in making the right choice for our system. Now it's your turn. Analyze a given project requirement and decide which architectural pattern would be the most appropriate. Consider factors such as scalability, cost, and ease of deployment. Justify your decision based on what we have discussed today. To wrap up, we have explored several architectural patterns and their respective strengths and weaknesses. The takeaway here is that choosing the right architecture depends on the specific needs of your project, including scalability, complexity, and the skills of your development team. A good understanding of each pattern is crucial for making informed decisions. Thank you for your attention. If you have any questions or need further clarification, now it's time to ask. Let's have a discussion on any points that might need more explanation.